In this lecture, let us talk about the design of counter. First, let us know what is counter. A counter is a sequential circuit that follows the prescribed sequence of states depending upon the input pulses. And these input pulses could be a clock pulse, also known as a clock pulse, or these may originate from some external source, occur at prescribed intervals. Uh, these counters can be found in a lot of digital circuits, for example, in digital clocks, uh, moreover, in traffic signal, uh, these counters works, and many other digital circuits. Furthermore, we divided the counter into two types. One is known as synchronous counter and other is known as asynchronous counter. In synchronous counter, the flip-flops have a common clock pulse. These have same clock pulse. Uh, Therefore, all the flip-flop trigger at same time. Uh, Furthermore, these have high speed as compared to asynchronous counter. In asynchronous counter, the flip-flops have different clock pulses. All the flip-flop trigger at different time. Therefore, these have low speed. The figure 1 shows the schematic of the synchronous counter. Here it is comprised of 4 JK flip-flop. So it would be a 4-bit counter. Uh, so it is obvious from this fig that the clock pulse is same for all the counters. So at same interval of time, at same time, all the flip-flop will toggle or the uh, will will work. I mean, the next state will achieve at same time for all the flip-flops. So uh, taking into account the figure 2, here we see that uh, the uh, the all 4 flip-flops have different clock pulses. Here the input uh, of first, flip-flop is the clock pulse of second flip-flop, and so on. So uh, these flip-flops work at different clock pulses. Therefore, uh, these have low speed as compared to synchronous flip-flop. Uh, Now let us talk about binary flip-flops. So what are the binary flip-flops? Sorry, uh, I'm talking about the binary counter. Now we are talking about binary counter. The binary counters count the binary number. Uh, if we have n-bit binary counter, then we will use n flip-flop. Suppose n-bit. Oh, sorry. Okay, n-bit binary counter. N-bit binary counters have n flip-flops that may count from 0 to 2 raised to power n minus 1. So If suppose we have 3-bit counter, then we can count from 0 to 2 raised to power 3 is equal to 8 minus 1, 0 to 7. In this lecture, we will discuss 3-bit binary counter. Suppose we have a 3-bit binary counter. Okay, 3-bit binary counter. It would be comprised of 3 flip-flops. So, and it will count from 0 to 7, or from 00 to 001 up to 111. Okay, this is the state diagram for 3-bit binary counter. Suppose initial state is 000, and the next state it would be when it will count. So the counter work on the clock pulses. As the next clock pulse will come, the next state it will change the state from 00 to 001. So it is the next state. Present state is 00. Now the present state is 001. The next state would be 010. Here the present state is 010. So the next state is 011. Again the next state, sorry, uh, the next state is 110. The present state is 001. The next state is 100. So then again the next state is 101, and next state is 110. So this is the 110. Again the next state is 111. So finally this 111 state will change to 000. So the counter will keep repeating. So as initially, let us start from 000. As the next clock pulse will arrive, so the counter will shift to the next state 001. Now we can say that the present state is, suppose the present state is, we have the present state and next state. Let me draw the table. So we have a present state and next state. So A2 is the most significant bit here, then A0 is the least significant bit. So this is the present state, this is the next state. A2, A1, A0. We have a 3-bit. So suppose we will start from 000. So our present state is 000. Then its next state, if we will start from present state 000, the next state is 0 0 1. Now the present state is 0 0 1. Its next state is 0 1 0. So the next state is 0 1 0. Here the present state is 0 1 0. So this is the present state. Next state would be 0 1 1. Okay, I will design a 3-bit counter by using T flip-flop in this example. So you can use some different flip-flop. So next, the present state is 0 1 1. The next state is 1 1, sorry, 1 0 0. Present state is 1 0 0. The next state is 1 0 1. If present state is 1 1 0, sorry, 1 0 1, the next state is 1 1 0. So here present state is 1 1 0. So what would be the next state? It would be 1 1 1, right? Now the present state is 1 1 1. The next state is 0 0 0. So this table shows the present state and next state of the counters. Now I have to use T flip-flop to design this synchronous counter, 3-bit synchronous counter. As I already told you guys that the excitation table for the flip-flop is very important. So now we have given the present state and the next state, and we have to decide what would be the input of the flip-flop. So uh, let me uh, redefine the excitation table. This is the present state. This is the q of t plus 1 is the next state. So the inputs, here is the input for T flip-flop. When present state is 0 and next state is 0. When there is no change, then the input would be, flip-flop input would be 0. When there is a change from 0 to 1, present state is 0, next state is 1, so that there is a change, so the input would be 1 here. For 1 0, present state is 1, next state is 0, so the input would be 1. There is a change. Present state is 1, next state is 0. So when present state is 1, next state is 1, there is no change, so the input would be 0. So here we have a 3 flip-flop. So because we have a 3 bits, I will use 3 inputs. So this is the input TA2, this is the input TA1 for, and this is the input TA0. So this is for the TA0 is the first flip-flop, TA1 is the input for second flip-flop, and TA2 is the input for third flip-flop. So here first we have seen that when A0 is 0 in present state, the next state it is 1. So the input should be 1 here. And here you can see that the present state is 0, next state present state is 1, next state is 0. Therefore the input should be 1 in this case. Where by taking this case, when input is present state is 0, next state is 1, so the input would be 1. Here present state is 1, next state is 0, so the input is 1. As you can see here, the present state is 0, next state is 1, so there is a toggle, so the input would be 1 here. Again, we have present state is 1, next state is 0, so the input is 1 here. Here present state is 0, next state is 1, so the input is 1. Present state is 1, next state is 0, so the input is 1 over here. Now taking into account the second bit here, the present state is 0, next state is 0, there is no change, so the input would be 0. Here the present state is 0, next state is 1, so the input is 1. Present state is 1, next state is 1, so there is no change, so the input would be 0. Present state is 1, next state is 0, so the input is 1 over here. Present state is 0, next state is 0, there is no change, so the input would be 0. Here the present state is 0, next state is 1, so input is 1. Present state is 1 and next state is 1. This one is the present state, this one is the next state, so the input is 0. Here present state is 1, next state is 0, so the input is 1 here. For this bit, for A2, so here we know that present state is 0, next state is 0, so there is no change, the input is 0. When present state is 0, next state is 0, there is no change, again input is 0. Present state is 0, next state is 0, so there is no change. Here you can see the present state is 0 and next state is 1. So there is a change, so we will incorporate here 1. So the input is 1. Here the present state is 1, next state is 1, no change, so input is 0. Present state is 1, next state is 1, no change. When there is a change, you will incorporate the input as 1. So 0. Here input present state is 1, next state is 1, there is no change, so the input is 0. Present state is 1, next state is 0, so the output is input is 1 here. Now I will simplify these tables by using Carney map, so we'll get the simplified expression for these inputs TA2, TA1 and TA0. So let me erase this uh, 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 state diagram. So this is called the state diagram. State diagram, the one is state and diagram. State diagram explain the state, present state and next state, and this is the state table. State table. So I will reduce the state table by using Carney map. So uh, I'm going to erase the state diagram. So here and this characteristic, excitation table, I'm going to remove. Now let me use the Carney map method to reduce the state table. First, let me find the expression for the input TA naught. So this is TA naught. This is the present state. I will take this this truth table into account, and corresponding outputs are TA naught, TA1, TA2. These are the inputs for uh, T flip-flop. So let us reduce TA naught. So here I will incorporate TA1 and A1 and A0. Here I will incorporate A2, most significant bit. So it could be a 0 or it could be a 1. So there are 4 combination here: 0 0 0, 0 1, 1 1 1, and 1 0. So when there is a combination, you can see here when we have a when we have a 0 0 0, so the output here, this input of flip-flop A naught is 1. When there is a 0 0 1, so TA naught is 1. When there is a 0 1 1, T naught is 1. When there is 0 1 0, it is 1. When there is 1 0 0, 1 0 0, it is a 1. For 1 0 1, it is a 1. For 1 1 1, it is a 1. For 1 1 0, it is a 1. By simplifying this by Carney map, I will get T A naught is equal to 1. So this is the simplified expression for TA naught, which is equal to 1. Next, let us simplify TA1. So again we have 8 boxes. TA1. So this is the combination for A1 and A naught. Then 0 1, 1 1 1, 1 0, 0, and 1. So here you can see when combination is 0 0 0, the TA1 is 0. For 0 0 1, it is 1. For 0 1 1, it is 1. For 0 1 0, it is 0. And for 1 0 0, it is 0. For 1 0 1, it is 1. Here you can see. For 0 1 1, it is 1. 0 1 1, you can see here it is a 1. 1 1 0, it is a 0. Now by simplifying this K map, now this column will be simplified. A prime will simplify, A2 prime will simplify with A2, and here A1 prime will simplify with A1. So I will get TA1 is equal to A naught. Next I will simplify TA2. So this is K map for TA2. And these rows is for A naught and A1. So there are four combinations: 0 0 0 0 0 1, then 1 1 1, then 1 0. Here we have 0 and 1. So here we can see that this is 1 for 0 1 1, this is 1 for 0 1 1, and this is 1 for 1 1 1. So for remaining combination, TA2 is 0. By simplifying this Carney map, I will get TA2 is equal to, this is equal to uh, this is equal to A1 and A0. So these are the simplified expression for the inputs of the flip-flops. Now let me draw the counter. So we have a synchronous counter. So it is comprised of three flip-flops. We have three flip-flops. So these have the common clock pulse. So I'm making a common clock pulse. So this is the clock pulse. Furthermore, these have uh, three outputs. So outputs are with the red line. First is A0. For this is the first flip flop. This is the second flip flop. Its output is A1, and this is the third flip flop. Its output is A3. Now the inputs for this flip flop is TA0, and its input is always, so I will use a different color for inputs. I'm using a green color for input. This is always 1, and input TA1. So which is A0. So I will connect this output with the input of second flip flop. Now this is the input for TA2, and this is equal to the A1 and A0. So I will use this A1. I will this is the A naught. So I will add these outputs, and it would be the input of A2, sorry, TA2. So TA naught is always 1. So let us start. Okay, let us analyze. Uh, uh, let us analyze this flip flop. Sorry, this counter. So let us start from 0, 0, 0. Firstly, all the output are 0. This is the present state. So what would be the next state when TA naught is equal to 1? So present state is equal to 0. So what should be the next state when the input is equal to 1? So the next state should be change, should be 1. So uh, here the input is the output of A naught. So this was 0. So present state is 0. So the next state would be 0. So uh, for TA2, its input is uh, the AND gate, and is the AND of A1 and A naught. So here A naught is equal to 0 and A1 is equal to 0. So its output would be 0. So the input A2 is equal to 0. Therefore, there would be no change. For next state, it would be equal to 0. So now these are the present state 0, 0, 1. So here when we have a 1, 1 is the present state. So the input of this flip flop is 1. So next state, what would be the next state? It would be 0. As the clock pulse will arrive, the second clock pulse will arrive. So the next state would be the from 1 to 0. It would be 0. So here taking into account the second flip flop, its input was 1 because this output A naught is equal to 1 here. So it will toggle. The present state was 0, so the next state would be 1. So here uh, this AND gate, it has one input is 1 and other input A1 is 0 here. So the product, so the output of this AND gate is 0. So the input of TA2 is equal to 0. So as the present state is 0, so the input is equal to 0, there would be no change. Now as next clock pulse will arrive here present state is equal to 0. Here input is, for this flip flop the input is 1. So the next state would be 0. So here for this flip flop the present state is 1 and its input was 0. So there would be no change, the output would be 1. For this flip flop uh, its one input was 0, one input was 1. So this AND gate output is 0. So the input of this flip flop is 0. So the present state is 0. Next state would be no change. It would be 0. Now taking into account the as next clock pulse will arrive, uh, then this counter will uh, switch to next state. Here present state is 1, input is 1. So this flip flop will toggle. So the next state would be 0. Its input for this flip flop, its input was 1, present state was 1. So the next state would be 0 for this flip flop. So its input would be 1 in this now because both the inputs for this AND gate are 1. So this input was 1, the next present state was 0, next state would be 1. So in similar fashion, eventually you will get so on, so on. Eventually you will get 1, 1, 1. When there is present state is 1, 1, 1. So here this present state was 1, its input was 1, so the next state would be 0. This present state was 1, input was 1 because this output is the input of this flip flop, so the next state is 0. These 1 1 1 a naught and a1 are the input of this AND gate, so the output is 1. As input of this flip flop is 1, present state was 1, so the next state would be 0. In similar fashion, this will keep on moving, from 0 0 to 0 0 1 and so on, 1 1 1, then it will happen 0 0 0. So this is the 3-bit sequential binary counter. You can design this counter with the help of JK flip-flop. Similarly, you can design a 4-bit flip-flop. In next lecture, we will talk about asynchronous flip-flop. That's it. Thank you so much.